right, so Atterberg limits, huh? Big part of this GRTC exam, right?
Oh, definitely. Always seems to come up.
Yeah, and I think I get the basics, like how it relates to how the soil changes with water.
Right.
But some of the details still feel a bit, I don't know.
Muddy.
Yeah, a little muddy.
Makes sense. It's foundational, but even, for someone who's been doing this a while, a refresher never hurts, right? Especially with this exam.
Exactly. So I pulled up this Atterberg limits in geotechnical engineering, this excerpt.
Okay.
It's dense, but hopefully, we can pull out the key stuff we need, what we really got to know, right?
Yeah, let's cut through the jargon, get to the good stuff.
All right, so first things first, definitions. The book lists 4 main ones: liquid limit, plastic limit, shrinkage limit, and plasticity index. Mm-hmm. Are all those, do we need to know all those in detail for the exam?
Oh, absolutely. All fair game. Yep. Think of it this way. Soil, it can be a solid, it can be like a moldable material, or it can be a liquid, all depending on how much water is in it. And these Atterberg limits, they tell us where those transitions happen, where it goes from one to the other.
Okay, yeah, that makes sense. So liquid limit, LL, that's basically like when soil turns to soup.
Basically, yeah, it's the moisture content where it goes from a plastic state to a liquid. Like you can't really build on soup, right?
Definitely not, no. So plastic limit, PL, is that more like, I don't know, Play-Doh? Like moldable, but still holds its shape.
Perfect analogy. Yeah, that's it. It's the moisture content where it goes from kind of semi-solid to that workable plastic state.
Okay, I'm with you. What about shrinkage limit then? SL. The book mentions cracking, so I'm guessing it's like how dry the soil gets before it basically turns into like a rock and starts breaking apart.
Yeah, you nailed it. So it's the moisture content where if it dries out anymore, it's not going to decrease in volume anymore. Think about dried out mud, how it cracks. That's basically what's happening. It's hit that shrinkage limit.
Okay, makes sense. Okay, last one. Plasticity index, PI.
Yes.
The book says PI equals liquid limit minus plastic limit.
Right.
So it's not something we measure directly. We just get it from those other two.
Exactly. It's derived from the other two. But don't underestimate how important it is.
Okay.
It tells us that range of moisture, right? Where the soil is in that workable, that plastic state.
So like for construction, if you have a higher PI, that means you've got more wiggle room, like with the moisture before it becomes a problem.
Exactly. Yeah, it's a crucial indicator of how that soil is going to behave. For example, if you've got a high PI, you might be dealing with, expansive clay, which is not fun for foundations, right?
Right. Yeah. Okay, that's making more sense now. So we know what these limits are, but how do we actually figure them out? Like the book gets into these pretty specific lab tests.
Right.
Do we need to know all the nitty-gritty details of those for the exam?
I would say you definitely need to understand the principle behind them, right? And what they're telling us. Like some questions might ask you to even interpret the result.
Okay. All right, good to know.
Yeah.
So what are the main tests, like the ones they use?
Okay, so for liquid limit, the classic one, it's called the Cassegrain cup test.
I've heard of that. It's the one where you keep dropping the cup of soil and see when it smushes together, right?
That's the one.
It seems kind of low tech, honestly.
It is. It's a little old school, but it's still widely used. You've got your brass cup soil sample, you cut a groove in it, and you repeatedly drop it until that groove closes. The number of drops and the moisture content help you calculate that liquid limit.
So fewer drops means a higher liquid limit because it takes less effort to get it to flow.
Exactly. Okay. And then there's the cone penetrometer. That one's a little more modern.
Okay.
And with that one, you're basically measuring how deep a standardized cone sinks into the soil at different moisture contents.
Okay. So instead of counting drops, you're measuring penetration depth.
Right.
Sounds a bit more precise.
It often is, yeah. Less room for, human error. Now, for the plastic limit, we get even more hands-on.
Oh, is this the one where you roll the soil into those little, tiny little snakes?
That's the one. Yep.
Yeah.
You roll it into a 3.2 millimeter thread, and the moisture content where it crumbles, that's your plastic limit. So it's telling you how much it can deform before it cracks.
Okay, I can actually visualize that one. That's pretty straightforward.
Yeah.
What about shrinkage limit? The book mentions oven drying, so we just bake the soil for that one.
Essentially, yeah. You dry a prepared soil pat in an oven. You measure how much it shrinks. And that shrinkage limit is the moisture content where it stops shrinking, basically.
It's all about volume change, right? How much is going to change as it dries?
Okay, so we've got our definitions. We know kind of the basic idea behind the tests. But why why do engineers actually care about this stuff?
Right.
Like, how do we actually use this on real projects?
That's where it gets really interesting. Remember all those soil classification systems they drilled into us back in undergrad?
Oh, yeah.
Atterberg limits, they're like a cornerstone of those.
You mean like the Unified Soil Classification System, USCS and AH?
Exactly.
Okay.
So knowing these limits helps us categorize the soils, which is like the first step in understanding how they're going to behave under different conditions.
But it's more than just like slapping a label on it, right?
Right.
Like, we need to know how it's actually going to react in a real world situation. Absolutely. And that's what we're going to dive into next. Like, how do Atterberg limits help us predict that behavior and make those decisions on the projects? This is the stuff that's really going to help you on that exam.
Perfect. All right, I'm ready for part 2.
So yeah, you're right. Knowing the classification is important, but it's just the beginning. Like, the real power of this stuff is predicting how it's going to actually behave on a project.
Okay. Yeah, because that's what I need help with. It's connecting those dots, right? Like from the lab test to the actual job site.
Right.
So how do we go from knowing these PLPI numbers to making decisions about like foundations or slopes, all that?
All right, well, let's start with foundations. Remember those expansive clays we talked about, high PI soils?
Yeah.
Those guys, they're notorious for causing foundation problems because they swell and shrink so much with changes in moisture.
Yeah, I remember from class. Like an uneven sediment, cracking, damage to structures, all that.
Exactly. So if you're designing a foundation and, you've got a high PI soil, you got to take that into account. Might need a deeper foundation or a different type altogether to handle those volume changes.
So like a shallow foundation might be okay for a low PI, but high PI, you got to go deeper to reach like more stable ground.
Exactly. You might even need to look into ground improvement techniques to stabilize the soil before you even start building.
Okay, that makes sense.
Yeah.
So are there any like rules of thumb we should remember for the exam about PI and foundations?
Well, it's not quite as simple as just memorizing numbers. You know, it always depends on the specific soil and the project. But generally speaking, soils with a PI greater than 20, those are considered highly plastic, and they require more careful consideration for foundations.
Okay, good to know. So high PI, I think expansive soils, potential foundation issues.
Right.
What about low PI soils though? Are those always good news?
Not necessarily. While they might be more stable in terms of volume change, they can sometimes be really hard to compact properly.
I see. So if you need to get a certain density for your foundation, a low PI soil might require way more effort to compact it down.
Precisely. And if you don't compact it enough, you could end up with settlement problems down the road.
Right. Okay, so Atterberg limit's important for foundations. What about slopes though? Because I know landslides are a huge concern, and the book mentioned Atterberg limits being a factor there too.
Absolutely.
Okay.
Think about what happens during a landslide. Soil gets saturated with water, loses its strength, starts to flow.
And the liquid limit tells us like how much water it takes for the soil to reach that like flow state, right?
Exactly. So if we know the LL of the soil on a slope, and we know how much rainfall the area typically gets, we can actually assess the risk of a landslide happening.
So soil with a low LL is more susceptible to landslides because it takes less water to reach that like critical point.
Exactly. It's like having a smaller margin of safety. And the plasticity index comes into play here as well. A high PI generally means the soil is more cohesive and less likely to slide.
So like a steep slope with low LL A&D, low PI soil, that'd be a big red flag.
You got it. That's a recipe for potential disaster, especially in areas with heavy rainfall.
Okay, this is all starting to make a lot more sense. Now we've talked about foundations and slopes. Any other like major areas where Atterberg limits are crucial in the exam?
Definitely pavement design. Remember, a road is essentially a structure built on soil, and that subgrade, the soil beneath the pavement layers, it needs to be stable to support those traffic loads.
So just like foundations, we got to think about swelling and shrinking.
Exactly. If the subgrade soil has a high PI and swells when it gets wet, you could end up with pavement cracking. Unevenness. On the other hand, if the subgrade's too loose and easily compacted, you could get running potholes, all those fun things.
Right, so we got to find that sweet spot.
Right.
Like a subgrade soil that's stable won't cause problems with the pavement.
That's the goal. And Atterberg limits help us select the right materials and design that pavement structure to achieve that.
Okay, this has been super helpful. I'm starting to see how those lab tests we talked about like actually translate into real world engineering decisions.
Good. I'm glad to hear it. But let's take it a step further. The book briefly mentions climate change. How do you think that might impact the way we think about Atterberg limits in the future?
That's a good question. Well, we know climate change is causing more extreme weather events, right? Like heavier rainfall, more frequent droughts.
Exactly. And both of those extremes can really impact soil behavior.
So, for example, if an area is getting more intense rainfall, a soil that was previously considered stable might suddenly become way more susceptible to landslides.
That's a very real possibility. And on the flip side, in areas with prolonged droughts, soils with high shrinkage limits could see more cracking settlement issues, all that stuff.
So it's like the rules of the game are changing, and we need to adapt our understanding of Atterberg limits to keep up.
That's a great way to put it. It's not just about applying what we know now, it's about anticipating how those limits might become even more important as our climate changes.
Wow, that's a lot to think about. So it's not just about passing this exam, it's about being prepared for the challenges that are coming up as engineers.
Absolutely. And speaking of the exam, there's another concept related to Atterberg limits that often trips people up. The activity of a clay. Have you reviewed that yet?
I've seen it mentioned, but honestly, I'm not entirely sure what it means or why it matters.
It's an important one, especially when you're dealing with those fine-grained soils. Want to unpack that a bit?
Definitely. Dive into that. Okay, so activity of clay. We were talking about that.
Right.
I haven't really gotten that yet. Like, what's the big deal about it?
Well, it basically tells you how sensitive that clay is going to be to changes in water content. Like some clays are pretty chill. They don't change much even if they get wet or dry out. Others are like super reactive. They swell up like crazy when they get wet or shrink and crack when they dry.
So is it kind of like plasticity index, but specifically for clays?
You're on the right track. Remember how PI tells us that range of moisture where the soil's workable? Activity zooms in on clays and tells you how MUCH they change within that plastic range.
Okay, that makes sense. But how do we calculate it? The book mentioned something about plasticity index and clay fraction.
Exactly. It's a pretty simple formula, actually. You just take the plasticity index of the soil and divide it by the percentage of clay particles.
Okay.
So higher PI, smaller clay fraction means higher activity.
So a clay with a high activity is going to be more prone to those, like dramatic volume changes, the ones that can mess up foundations and slopes and all that.
Exactly. That's why it's so important for those applications. Like, it helps us predict how much it's going to swell or shrink. So we know how much movement we need to account for in our design.
Okay, yeah, that makes sense.
Yeah.
It's all starting to click now. Like, it's not just about memorizing definitions. It's about understanding how these things all relate to each other and the real world problems.
Exactly. And that's what the exam is really testing, right? Your ability to apply this stuff, not just spit out facts.
Right. Okay, good to know. I feel like we've covered a ton today. Anything else on Atterberg limits that we should absolutely make sure we know for this exam?
I think we hit the major points. Remember, focus on the principles behind the tests, how those limits relate to classification and behavior, and how it all applies to those real world challenges like foundations, slopes, pavements, all that.
Got it. And to think all this started with some pretty basic lab tests, huh? It's crazy how much we can tell about how the soil's going to act just from that.
It is. And remember, it's not just about the numbers. It's about what they tell us and how we can use that to make the right decisions as engineers.
Like being a soil detective.
Exactly. Using those clues to solve the mystery.
All right, well, I'm feeling way more confident about Atterberg limits now. Thanks for going through all that with me.
Anytime. And hey, if you hit any snags while you're studying, don't hesitate to reach out.
Definitely will do. And to everyone listening, good luck on that GRTC exam. We're all in this together.